The spirit of open source is alive in quantum computing. A group of universities is working on developing algorithms and software that could greatly improve the performance of practical applications. They're even working on benchmarking, which is important in identifying the real-world performance of quantum systems. Find out what's involved in squeezing everything possible out of quantum computers in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Today, our guest is a scientist from University of Chicago who also founded EPiQC. And he's also co-founder of a company that you're probably familiar with, Supertech. They were on recently with Pranav. So I'd like to welcome Fred Chong. Thanks for coming on.
Thanks. Maybe I should clarify. EPiQ isn't exactly a company. It's a sort of a research project, research center funded by the National Science Foundation.
Yeah, that's a good distinction. And it looks like you guys are involved with, I guess, 5 institutions. Is that correct?
That's right. There are 5 universities involved. And the reason it's so many universities is we try to cover the disciplines that span a large range of quantum computer science.
Great. Yeah, and I was looking. So your big hope is to, with what a lot of we're doing in this industry, is to get to a point where we can make practical use of these machines in the near term. That's sort of the grail here, right?
Yes, absolutely. And I think that a key factor there that we're focusing on is really building software that connects the algorithms or applications to the physics of the machines.
Yeah, so you're trying to go for more of a device independency, right? You envision some way that these applications can run on any kind of back-end target?
That is true. I mean, we want our software to be able to allow you to run on any back-end target. But in some ways, what we need to do is almost the opposite, which is we need to build software that can go to any target, but we need to be able to customize or tailor our software to be very efficient on specific physical devices.
Do you guys then go outside of the normal programming approaches, or do you at some point hand off to, so let's say if you were going to use an IBM target, at the very last step before the program goes to the quantum computer, it sort of gets rewritten and optimized to make sure there's no mistakes, nothing that will cause some kind of resource waste. Do you still do that kind of handoff at the end?
We tend to hand off at a much lower level. IBM actually does expose a method to essentially get almost directly to their hardware. And so we skip a lot of their steps and try to integrate the kinds of things they would do into sort of the upper levels of our software.
Oh, interesting. Okay. And do you envision allowing this to be accessible as a cloud environment where people could sort of play in your walled garden of sorts and then hand off to hardware targets?
Yeah, I think that would be the end goal. I mean, EPiQ is a research project, so all our code is open source and available to people, but we don't typically maintain services or cloud environments. People can use our code to set that up. The purpose of spinning out Supertech, which people heard about already, I guess, was to take that work and make it a more usable environment for customers and users.
Yeah, so I saw you have a GitHub and there's, I guess, 6 repositories there right now. Do you have anything that's coming soon there that you want to share?
Well, our work tends to add to those repositories. You can think of it as a big set of tools that are a stack of software that go from how the user would program an application down to specific machines and specific physical properties. I think what's coming up next is more integration of those techniques. What EPiQ has done in the first 3 years has found we've discovered really substantial techniques to make make programs more efficient, but we've explored them initially more in isolation, and we're trying to put them more together. If it's helpful, I could maybe give an example of one of the techniques so the listeners get a sense of what we do.
Yeah, absolutely. That'd be great.
Sure. So here's an example which is a little bit relevant to your question about how do we interface with IBM. A typical quantum program would be translated by our software, compiled down to quantum instructions that sort of look like, they look like the assembly level instructions for microprocessors, such as the x86 or Intel instruction set or the ARM instruction set. So normally we would go down to instructions and then hand that off to IBM. And then IBM would take those instructions and translate them actually into microwave control pulses. Sort of the kind of thing you would see in the lab on a scope, for example. And those would actually implement those instructions on the IBM machines. But it turns out that we can actually build software that directly translates programs into those control pulses, and that can be 10 times more efficient. So that's an example of how we basically take a shortcut and get more efficiency.
Yeah, we noticed that. Anytime we just try to run things at a default setting, we get one level of performance. And then when we try to go down to the pulse level, we could see the changes immediately.
Yeah.
So I think that will be more important. And I tweeted a while back about this company, Sandia Labs. They came up with Jackal, just another quantum assembly language. Yeah. So I don't know if you guys consider yours just another quantum assembly language.
Well, most of the work that we do does not define another assembly language at all. Right?
Yeah.
In the work that I described, we essentially skip the assembly language.
Mm-hmm.
In other work that we do, we just entirely change the way you think about the machine, right? So a typical quantum machine works on binary information, right? So you have quantum bits that are two levels, 0 and 1. And so we have done some work where we looked at the physics of many of these machines, and that allows us to represent three levels, 0, 1, and 2. And that's what we might call ternary logic or Q-trits. And that essentially lets you get more out of every physical device that a machine already gives you. And so that also sort of entirely changes the way that you think about how to do computation on that machine.
Yeah, I'm glad you brought that up because two things that immediately caught my eye were your mention of Q-trits and benchmarks. So I wanted to talk to both of them. So with the benchmarks, would that be what Pranav was kind of talking about when he was on? He was saying that they were working on something to help benchmark systems. So would it be that same code that's on GitHub?
Yeah, absolutely. We're definitely thinking about how to, as systematically as possible, design benchmarks for a range of quantum platforms and quantum applications. And there's a very rich tradition of benchmarking in sort of the classical computing community that we come from, and we're trying to bring that to the quantum community. And and one of the concepts is that each benchmark sort of hits a set of features that they stress test in a particular machine. And it's important to sort of identify those features and then come up with a suite of benchmarks that exercise different features in different ways, so that you get the sort of full range of advantages and disadvantages for different kinds of machines.
Oh, that's very interesting. So yeah, I remember, of course, the classic benchmarks. It would hit things like typical office applications, graphics, all those sorts of metrics. But with these benchmarks, then, are you looking to see not just how it handles certain types of algorithms, but maybe how, the T1, T2 times, how those might impact performance and which machines might be better suited to certain types of applications? Is it going to get that kind of deep to make predictive guesses as to whether one machine would be better than another at what kind of application?
Yeah, at some level, I think that there's a bit of an art to it right now, since there aren't actually a lot of quantum applications. Mm-hmm. But we'll be looking to find sort of well-motivated applications that stress machines in different ways. And then there is that connection that you can see that certain classes of applications care about certain things more than others. And for example, you mentioned T1, T2 times. Some applications will care about, many will care about what the error rate is on an operation, especially two qubit operation. Some may care about the connectivity of the qubits, and some may care about how many qubits you have, right? And so the different machines out there have different advantages and disadvantages in how they scale these different things. And so we're really looking to try to map out this space and define this, this vector of features.
Yeah, I think it's important, especially with quantum volume. When I was first exposed to it, I thought it was an interesting idea, but I don't know if I love it so much anymore. It feels like by tweaking certain things, you can get kind of outrageous numbers, right? Like IonQ right out of the gate, they were like, yep, 4 million quantum volume. It's like, whoa. The rest of us, at the time were 32 moving to 64. And of course, Honeywell just announced that they've hit 512. But So how do you feel about quantum volume?
Well, I think quantum volume was a very interesting metric in the early days of quantum machines, right? It had some nice things about it, right? It specifically stresses the connectivity of the machine, which is something that many benchmarks, certainly back then, did not do. Mm-hmm. And so I think that was a great thing. But quantum volume was really designed for the early days of machines, and it has an exponential in it that makes its numerical value really large. And so as machines improve, that exponential starts making the metric seem a little silly. And it is also a very, it's a specific kind of benchmark, and it doesn't have this variety of stress tests that I think we need as we move forward.
Yeah, and at the end of the day, it's not even though they're working with it for so long, IBM isn't really touting quantum volume anymore as their news story, right? Witness what they predict for 2023. Condor, 1,000 qubits. They didn't really talk about quantum volume. They talked back again to what everyone really likes to report on in the early days. So I wonder if there's something new that we need to do. Just say how many qubits and then some kind of like quality value or something that tells the whole story.
Yeah, I think that we definitely need to move forward. And if you think about it, the benchmarking in classical computation followed the same evolution pattern, where in the early days you could just look at the rate that you could run instructions, or the rate at which you could run arithmetic or floating point operations. But as things progressed and became more complex, we had to define different benchmark suites, and then potentially come up with scores for well-known suites that sort of summarize the ability of machines to run on those suites. But you really needed this diversity of benchmarks and essentially these different stress tests to really get at the properties of the machine. And the honest truth is that as machines become complex, there's no single number or even two numbers that you can use to characterize a machine.
Yeah, I agree. I just know that in my gut, I would never feel comfortable telling someone that IonQ's machine is 65,000 times more powerful than an IBM one. I don't think I can make that argument. That's where it starts to feel currently limiting. Yeah.
Since quantum volume has an exponential built into it, really to make the early improvements sound bigger.
Yeah.
You should just take the log of that value to make it a little more realistic.
Yeah, I agree. It's pretty soon it'll be like quantum volume of 10 to the 700. Yep, we're set. We still can't crack encryption, but it'll be something like that.
Yeah.
So on the EPiQ site, they talk about a physical machine with 100 quantum bits expected in the next 3 to 5 years. And I feel like we've pushed the envelope a little bit. I think we're going to be a little farther, right? Like IBM, their plans, IonQ's plans seem pretty aggressive too. They just went public, right? And they have some cool plans about that kind of interconnect idea. Can we get these machines to work together? So So I believe personally in like 2 years, we're going to have way more than that. I think we will have about 1,000 qubits guaranteed pretty much. Oh, there's no guarantees, but I think we'll be pretty close to that. So do you feel that 2023 is this sort of tipping point year, the year of advantage that we're going to see?
We hope so. I will say that you point out a shortcoming of our academic project, that that epic little blurb description that you looked at was written 3 years ago when the project started. And so when you say 3 to 5 years, yeah, we are at pretty close to 100 qubits right now, which is remarkably prescient, I suppose. I would say that we definitely hope that soon we'll reach a tipping point. It's easy, and I think that's why in the roadmaps you see this. It's easy to think about how many qubits we can get. It's a little bit harder to think about how reliable they will be and how reliable the operations will be, and how good the interconnect will be. But certainly getting to 1,000 qubits will be very useful. And presumably, some of the vendors will get to a point where the operations and the connectivity is good enough to utilize those 1,000 qubits in a good way. So I think, I am very optimistic that in that time frame we will get to something exciting.
Yeah, that's why I'm so excited about benchmarks in general. I love the idea. I would like to see something really standardized that everyone starts to use. There's a lot going on right now with IP, right? Like everyone starts developing to a point and then they're like, nope, this is ours. And then they take it sort of offline. It makes you wonder like what's going on behind closed doors. We don't know what advances. Everyone's basing it on the same few papers that were written when all this started. And they're just going from there with optimization or machine learning. They're just kind of like drilling in. Do you see any kind of more shared approach to development coming? Do you see any sort of groups forming, alliances or whatever that will try and push this industry forward a little bit more before we get to the closed door kind of secrecy that I'm starting to see already?
I think that, one way that the industry seems to cooperate fairly well is that the platform and hardware-centric companies tend to collaborate well with the software companies because they're in a little bit of a different business. And so obviously the hardware companies, in terms of their device technology, some of that is going to be confidential and they refine their technologies in their own way. But I think that how we use those technologies, there is a fair amount of openness at the sort of algorithms and software level that allows us to share a fair bit. And there's IP generated, but typically even with software and algorithms that have IP associated with them, the field is still fairly academic. So you do see the papers eventually about those things, and that does allow you to build upon that work. And so, I think, there is definitely a move towards commercialization and some competition, but I do see still a fair amount of openness. And I think there's there are some hybrid areas, it's in this sort of level of error correction, error mitigation, which sort of sits in between software and hardware, and that field is probably somewhere in between, where it's somewhat open, but where it starts crossing into hardware characteristics, maybe it's less open.
Yeah, I know you guys are working a bit on program verification and validation. I don't know if you want to talk about that a little bit.
Sure. It's a difficult area.
Yeah.
First, I'll start with the motivation, right? So we have a lot of, in classical computation, we have a lot of technology for verification, formal verification of programs and software. But typically in the classical world, it's viewed as a little cumbersome and difficult, and most classical methodologies resort to testing of machines and testing of software rather than formally verifying very much of the hardware or software. The problem with quantum machines is that we're trying to build machines of a scale that's inherently more powerful than classical computers, which means it's very hard to use classical computers to verify them or the software that runs on them because they're hard to simulate. And so at some level, we're setting ourselves up for a problem in which we can't test software and hardware very well for correctness, which means that there's a much higher value in terms of formally verifying things. And in fact, we're going to be pushing the limits of technology and building machines that are fairly noisy and error prone. And the first thing we're going to do is we're going to run software and applications on those machines. And it would really help us to know when we hit errors, whether the error is coming from the hardware or from the software. And so we fundamentally are very motivated to solve this problem. On the other hand, solving this problem completely is quite hard, right? In fact, if I could verify a quantum program very well, and that verification involved enough information that basically I could figure out what the answer of the quantum program would be, then I would essentially be doing the same thing as the quantum program's computation. And if I could that means that if the quantum program is solving something very hard, then the verification should be very hard. Or conversely, if the verification can be done in a short amount of time on a classical computer, then the quantum program is essentially not doing anything useful. So it's a very hard problem. But I will actually relate an experience we had, which was quite positive, which was we used some verification technology called an SMT solver, or a modular theory solver. And we were able to verify not a quantum computation, but IBM's quantum compiler. And we're actually able to find 3 bugs in the compiler, which have since been fixed, but were contributed by people through the open source mechanism, right? Mm-hmm. And so because it's an open source compiler, and it is a quantum compiler, which is hard to think about sometimes, it's actually really useful to have a verification mechanism to verify the things that people contribute.
Yeah, with open source, the idea is more eyes on code, to spot bugs and things. But in this case, you needed non-human eyes on code to spot it.
That's right. And in particular, there are certain things that are more subtle in quantum machines that eyes on code isn't necessarily going to easily be able to find. And also it's hard to test. Yeah, so when Feynman first thought about quantum computers, he was thinking the only way to simulate the quantum universe is with a quantum computer. And now we're at the point where the only way to validate that we're simulating a quantum universe is with another quantum computer on top, in a sense. So we just added one more layer here. Yeah, ideally that in the future that may be the case. Right now we're so early days that I don't think we could imagine verifying a quantum computer with another one that's just as unreliable. So we're really trying to develop the technology to do it with classical computers, but in a limited sense.
Yeah, that's interesting, because it's hard to imagine verifying once we blow past the ability to simulate how we're going to be able to keep up.
That's true.
Yeah, it's going to have to be something different's going to have to be done, right? Because we're almost at the limit now. We can't simulate. Probably the machines coming online later this year or early 2022, I would say we won't be able to simulate them.
That's right.
Yeah, we're going to be past that point. We're already going to get to that point where you'd need to convert every molecule in our solar system to a computer to even try. So we're not even close to having that kind of capability. Is there anything being done more at the University of Chicago that doesn't, maybe not even necessarily associated with this kind of joint project in this space? Is anyone working on research projects there to sort of solve these problems too?
Absolutely. I mean, EPiQ is actually just a piece of the very large efforts at the University of Chicago in the quantum space. EPiQ, I think, represents at some level the predominant sort of software efforts in the country, actually. But we're when you look at emerging technologies and materials and quantum communication and quantum sensing, we actually have an entire school of molecular engineering that works on these things. And in fact, in partnership with Argonne National Laboratory, which the University of Chicago manages, we lead one of the 5 Department of Energy National Quantum Initiative centers. And those are actually $110 million centers, which involve hundreds of researchers. And so the efforts in the quantum space are really substantial. And in fact, Chicago is the only area that has 2 of the NQI centers. Fermilab, which is also managed by the University of Chicago, leads one of the other National Quantum Initiative centers of the same scale, focused on quantum materials.
It's really interesting to me. I'm in Manhattan, and I feel like every podcast I do, I'm going to end up mentioning Chicago because so much is going on there. So, it's not by accident. We have this strong alliance with Chicago Quantum Exchange, and there's just a lot going on there. So I guess it's nice to see the Midwest getting its props, so to speak, and becoming this. Everyone used to talk about creating a new Silicon Valley, right? A Silicon Valley of the Midwest. I think pretty soon it's going to be more important to be this, which is definitely not limited by what Silicon Valley was. Quantum's going to be, obviously I believe in it strongly, or I wouldn't be doing what I do.
Sure.
Here.
Yeah, there's definitely an intention in this area to produce a quantum industry, much as Silicon Valley has done for classical computation. One thing I will mention also in terms of these efforts, there is a strong need to sort of train a new kind of scientist and developer, right? That sits at the intersection of computer science and physics and materials. And here at Chicago, they have degrees in quantum engineering, which at the moment are a little bit more focused on the lower end of that sort of physics and materials with some work in systems. But I think, we're developing it, and with EPiQ, we're trying to develop a sort of computer systems discipline for quantum computer systems, which I think is really a critical need as all of these companies in the industry move towards more substantial hardware platforms. They're discovering that their sort of shortage is in the software stack and how they make use of those platforms. And there's going to be a coming need already. There's a huge need for people trained in building software and systems that are aware of and understand the physics of these platforms.
Yeah, and I think that's going to abstract out a little bit eventually, right? Like in the early days, I feel like you really had to understand computing to program back in the early days. And everything was so manual, go all the way back to punch cards or whatever. But I do believe one day we're going to get to this point where we can have a really solid developer program. Even if someone just wants a bachelor's, they should be able, in theory, to take enough quantum courses and coding courses that they're able to then contribute and adapt use cases to algorithms and actually be hireable, after those 4 years. I think I'm already seeing it. I mean, we're already seeing people just be pulled in who had no training. They're just sort of like ramping up in one of the development platforms and moving ahead. Would you agree?
Yeah, I think so. And there's definitely a need for that. But I'd also say that quantum computer systems, more than for classical systems, and even for longer than classical systems, I think will need some amount of understanding of the hardware and physics of the devices for the sort of the most advanced developers, right? And
yeah, like I said, that whatever that program is, it's going to have key quantum pieces in there.
That's right. And I think for the next 5 to 10 years, maybe probably more than 10 years, I would say, there will be a very strong need for people with some of that training to really get the most out of these machines.
Yeah. Are you going to be coming in and creating something new, a brand new way to implement an algorithm, or are you going to be coming in and helping out with something that a company does regularly? I guess that'll be a big defining difference. Are you going to be that one that can really revolutionize, or, just sort of come in like right now, there's plenty of software jobs, right? Where straight out of school, in theory, you could contribute. They'll just hand you off some little piece of a very known environment and you're going to work on that. Whereas with this, it's right now still very much the Wild West. You come in and you say, how can we take one of these 60 algorithms and make you money within 2 years? That's kind of the idea. And it takes a lot of careful thinking and planning to do that.
Yeah, absolutely. And of course, there's a range of people that will be needed. And in fact, probably the bulk of the people you need are just sort of quantum familiar or still somewhat quantum knowledgeable, right? And but there is probably, as the industry picks up, a fairly substantial number of expert developers that you're going to need, which is a little bit like the early days of computing, which is where we are for quantum computation. Mm-hmm. But it's actually the case that even classical computing is starting to reach physical limits such that there are developers that need to be aware of things like errors in classical computers even.
Yeah, quantum tunneling, not to go back to quantum again, but in a classical computer, obviously, if you make the traces too small, that little electron's not going to be where you need it to be to represent a 1 or a 0.
That's right.
It might hop the fence and be somewhere else.
And even more than the dynamic aspects of it, as you build very small classical devices, you get a lot of variation in the devices, so that the devices aren't very consistent. And so you need to start accounting for a machine that has lots and lots of bits and transistors, but they don't, they're not all good ones. And so that ends up being sort of it's an economic issue, right? You basically can't afford to only take the perfect chips. And mm-hmm. So you have to build software that can account for imperfect chips. And that's starting to, to look a little bit more like what we have to think about in the quantum space. And so, although quantum will progress and we will scale and we will get much better machines, it's a little bit hard to imagine a future in which quantum machines will be perfect, right? And so at some level, we will always build software that can accommodate for some of that noise and variation.
Well, depending on the week, the perfect quantum machine is the topological computer, and depending on the week, it either exists or it doesn't. That's what I'm finding. So that'll be the one we're all waiting for here. But yeah, even if that happens with classical machines, we're not going to have to be on the ratio of error that we're dealing with quantum. You need a lot of qubits to get a good logical one, right? So it's hard to imagine classical being quite that off in terms of transistors to good ones.
Yeah, and in fact, maybe a little bit of a misconception is that just because we have quantum error correction doesn't really mean that we can run a program forever or that reliable qubits are free. The length of a program that you want to run and the number of qubits you need really determine sort of the overhead of quantum error correction.
Absolutely.
And so you still want to optimize as much as you can. And a really exciting direction is actually how does quantum error correction, some of the things that people have come up with in a fairly theoretical setting, how does that interact with some practical things you can do to make the error lower physically on a machine? So I mentioned error mitigation. There's an interface between error mitigation and quantum error correction, which we haven't really figured out yet.
Well, I think that'll be a future award in the making, right?
Absolutely.
Anything in that space. So I guess we'll wrap up on that optimistic note. Thanks. Sure. Thanks so much for joining. This was really great. And I'm sure I'll see you at lots of CQE events going forward.
Absolutely. Yeah, thanks for having me.
That does it for this episode. Thanks to Fred Chong for joining today to discuss EPiC. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World. And maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also find information on our quantum services at www.protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.